spending 1 year with us. We are very pleased to have you here.
Thank you very much, Professor Carol. So this work has been done, in collaboration with my supervisor, Camilo Korjekva, and my two other collaborators from ICTQT, Professor Michał Horodecki and Tamoy Biswas. The way that I divided my talk is in 5 parts. So first, I'm gonna give you a brief introduction about the question that we want to address. Soon after, I'm gonna introduce the main framework in which we will address this question, which is the resource theory of thermodynamics. And then I'm gonna show you our results, which consist in 2 theorems. And very briefly, I'm gonna apply these results into 2 applications. First for work extraction, and second for thermal encoding of information. And then I will finish my seminar with a brief outlook. So let me start by stating a fundamental question in thermodynamics, which is what states transformation are thermodynamically allowed for a given system? In other words, what is the constraints underlying some transformation from the thermodynamic point of view? And what is the cost in terms of energy associated to this transformation? So for example, the laws of thermodynamics give us all the set of constraints that underlying a given transformation. The laws of thermodynamics are usually expressed in terms of thermodynamic quantities, a correspondence between thermodynamic quantities, and they are described in terms of state variables. State variables are a set of variables that describes my system. And I'm usually do standard thermodynamics, classical thermodynamics in a limit called thermodynamic limit. What does it mean? It means that my system is composed by some number of particles, and this number of particles tends to infinity. And also that all the processes are taken very slowly in the quasi-static regime, because I have always to keep the equilibrium, okay? And then the question, for example, I can imagine that my system is a gas inside of a chamber, and the states variable will be pressure, volume, and temperature. And although they are statistical by nature, they are well defined because we are in this limit in which n tends to infinity. These quantities are averaged, and fluctuations in this regime doesn't play any role. So the natural question is, what happens if I go beyond the thermodynamic limit? What does it mean to go beyond? It means that I don't want to look to a system in which the number of particles tends to infinity, but I want to look for a system which is composed by a finite number of particles, for example. Well, what we can see is that my state variables, it won't be well defined anymore because fluctuations will play a role because I'm far from this thermodynamic limit. So I need a new set of constraints if I want to think about what is the constraints associated with states transformation. So for example, just a motivated example, we can think that I want to extract work from n subsystems, and we know that by applying the central limit theorem, the average of work scales with n, while the fluctuations associated to the work will scale with the inverse of the square root of n. In other words, fluctuations will play a role. So what I can do is, let's imagine that now I'm gonna treat these thermodynamic quantities, for example, work, heat, and entropy, as stochastic variables. But again, thermodynamic will give me more restrictions because these stochastic variables will be described by some probability distribution function. So for example, some probability distribution function of the work, but these probability distributions, they cannot be arbitrary ones. They must respect some relations called by symmetry relations. And the symmetry relations is a collection of theorems called by fluctuation theorems. A very famous example of fluctuation theorems is the Jagiellonian equality, which allow us to express inequality from the second law as equality. And just to make sure, in this, we are in the non-equilibrium regime, okay? So since in this regime fluctuations play a role, we need a new set of tools to describe this system. And then another question is, what happens if we go a little bit further? What does it mean if I look to systems even smaller, such that now not only thermal fluctuations will play a role, but also quantum ones. I will be in a scenario in which I have the presence of quantum features. And then I can ask this question again: how thermodynamics quantities can be carried over to the quantum realm? What is the constraints underlying states transformations? One of the things that I can tell you, a spoiler about my presentation, is that in this regime, not only fluctuations plays a role, but also information. Information is a very meaningful quantity in this regime, because the thermodynamic quantities, I will show you these, can be expressed in terms of informational quantities. So with this, I can again ask the question that I started this transparency, which is, what states transformation are thermodynamically allowed for a given state in this regime? Well, we will see that the results that I'm going to show you today comprehends these two scales. We will be between this intermediate regime between classical and non-classical. And the way that I'm going to address this question about states transformation is by looking for how I can manipulate some resources under free operations, for example. And because if I think that thermodynamics is a theory of restriction, we know a mathematical framework to deal with these restrictions, which is the resource theory framework. So this question can be translated into a study in which I study how I will manipulate resources under operations that I can do it for free. So let me start telling you about the building block of our framework, which is the resource theory of thermodynamics. But first, let me remind you very roughly that in a resource theory is defined by three ingredients. First, the set of free states, the set of free operations, and the monotones. In our case, in my whole presentation, we will see this scenario. Which scenario? I have a system here represented by this blue circle. The system is described by some state rho and some Hamiltonian age. And this system is interacting with a thermal bath at inverse temperature beta. The thermal bath is described by a thermal distribution, here denoted by gamma and Hamiltonian age E, okay? Well, we know that if I take my system, couple with the bath, and let my system to relax in the asymptotic limit in which the time tends to infinity, my system will thermalize. In other words, if I have system and bath, I can always achieve the thermal equilibrium. So a free state of my theory is a Gibbs state, is a thermal state, which is denoted by this expression here, such this beta here is the inverse temperature of the bath, and Z is the partition function defined like this. In other words, every state which is not thermal is a resource state. Every state which is out of equilibrium is a resource state. So for example, this green ball here. So I'm using this funny notation for if the state is not red, it's not red balls, it's a state out of equilibrium, but it's red, or if it is red, it's thermal equilibrium. If you have a collection of small balls, you have a thermal bath. This is just to make it more simpler. Okay, and how about the set of free operations? Well, three operations of my resource theory will be modeled by thermal operations. Thermal operations are CP-TP maps defined as follows. So basically the idea is that I have my system. I will couple my system with the thermal bath. I will involve both under this joint unitary here. This unitary is called energy conserving interaction because it commutes with the Hamiltonian of the system and the Hamiltonian of the bath. And thermal operations are free because thermal operations encodes the first and the second law of thermodynamics because they satisfy two properties. The first property is that the thermal state is a fixed point, which means that if my state is given by a Gibbs state and I apply a thermal operation, I must return to the thermal state. Otherwise, I would be creating resource and I would be violating the second law of thermodynamics. Let me be more explicitly in explaining you this. So let's imagine that I have a thermal state, this red ball, I couple with the bath, I involve both under this big unitary here, and I have to return, I have to get a thermal state in the end. If not, imagine that the result of this is a state out of equilibrium. I could take this system out of equilibrium, couples with the bath again, let it relax, and during this equilibration process, I'm extracting work. And then I could repeat the same process. I could apply some thermal operation, take the system out of equilibrium and relax again. And by doing this, I'm creating a perpetuum mobile, or in other words, I'm violating the second law of thermodynamics. So we say that this first property encodes the second law of thermodynamics. The second property tells us that thermal operations are time translation covariant. What does it mean? It means that it doesn't matter if you first, let's say that you have system and environment, if you first involve system and environment via this big unitary, you trace out the system and then you involve system on time and measure the time. This is the same as involving the system first on time, then involving via this big unitary here, tracing out the bath and then measure the system. So in other words, these properties telling us that energy has been conserved. So the first law of thermodynamics is encoded in this second property. Okay, so basically here I have my two ingredients, the set of free operations, the set of free states and the set of free operations. And now my last ingredient my last ingredient is the definition of monotone. So a thermodynamic monotone is a function that maps the set of quantum states into positive real numbers with the inclusion of the zero. And a thermodynamic monotone quantifies the amount of resource that a given system has. So for example, to be a monotone, this function has to satisfy these two properties. The first property tells us that monotones are decreasing under thermal operations. And this has to be satisfied. Otherwise, by thermal operations, I'm creating resource. And we know that if I create resource, I'm violating the second law of thermodynamics. And the second property tells us that thermal states don't possess any kind of resource. So the monotone assigned to thermal state gives me zero. So, okay, so just to make it clear, because I've been mentioning resource, and by resource, I mean states out of equilibrium, okay? Perfect. An example of thermodynamic monotone is the relative entropy between rho and a thermal state. This quantity here is defined as follows. And this quantity has some kind of, this is the first time that we see a thermodynamic quantity being expressed in terms of an informational quantity. Because we will see in the next slide that this quantity here, called by non-equilibrium free energy, it's a generalization of the concept of free energy. And this quantity tells us how much work, what is the maximum work that you can extract from a system which is out. We already saw a connection between informational quantity with a thermodynamic quantity. Let me show you some other thermodynamic quantities which will be expressed in terms of informational quantity. So for example, I already mentioned the non-equilibrium free energy. And since this expression is the general one, I'm gonna call it only by free energy. And the free energy, if I, for example, open this term, what does it mean? It means that if I substitute here e to minus beta h over z, I'm gonna get this expression here. And from this expression, we can see why the relative entropy between a given state and the thermal state is called as a generalization of the concept of the free energy. Because look that the first term is basically the free energy associated to your state, while the second term is the free energy associated to the thermal state. And if we remember about classical thermodynamics, the maximum amount of work that you can extract from a given system is given by a free energy difference. So here I have a free energy difference, but so this quantifies the maximum amount of work that you can extract from a system which is out of equilibrium. But let me point it out that this entropy which appears here is the von Neumann entropy, okay? So the second quantity, the second informational quantity, which you have some thermodynamic interpretation, is the relative entropy variance. It is a quantity defined like this. Okay, and this quantity tells me about some fluctuations of a given random variable. So in this seminar, these fluctuations will be free energy fluctuations. But if the initial state here is pure state, these fluctuations becomes only energy fluctuations. And if we are computing this function between two thermal states, but with different temperatures, you have a quantity which is proportional to the heat capacity. The last informational quantity that I want to introduce is the relative entropy skewness, which is an expression defined like this. And this expression is a little bit tricky to interpret, but its interpretation is that this function is, this quantity is a function of the derivative of the heat capacity with respect to the temperature. So since we have the tools that I wanted to present to you, let me introduce you to the question that I'm interested, but let's start from the basic. Let me start by saying about the general problem in resource theory of thermodynamics, not specific to resource theory of thermodynamics, but here the problem that we are interested. So this problem is called the general interconversion problem. And this problem consists in asking whether there exists some thermal operation mapping some initial state rho to some target state sigma, while you are able to use the bath. So for example, you have some initial state, you have your target state and a thermal bath at inverse temperature beta, and you ask whether you can transform rho to sigma via thermal operations. So in this picture here in the left corner, it's a very nice illustration about this problem, because let's imagine that my initial state is this blue ball, my target state is this green ball, and then we can ask whether we can go from this blue state to the target state. And you see this arrow pointed to out of equilibrium states to equilibrium states. Why? Because every time that you make a transition, you are dissipating some amount of resource, okay? You are basically distillating some amount of resource. So for example, if you go from this state blue to the green state, the amount of resource that the state green has is less than the amount of resource that the blue state has. So this is kind of a distillation process. And thermal states are in the bottom, because from thermal states, you cannot go to anywhere because these states don't possess any kind of resource. Let me be fair and tell you that this is not a unique problem in resource theory of thermodynamics, but you can ask the same questions in different resource theories. So for example, in resource theories of entanglement, in which the set of free objects is all the separable states, the set of free operations are local operations and classical communications, and you can ask the same questions. Or for example, in the resource theory of coherence, in which the set of free objects are all in coherent states with respect to some basis, and or in the resource theory of asymmetry. Well, this is the question that we are trying to attack, whether there exists some thermal operation map rho to sigma. But let me tell you that the general answer for this question is not known beyond the simplest case, as it was pointed out in 2015 by Camille and collaborators. Although the set of necessary and sufficient conditions was found in 2013 in this paper by Michal and collaborators for a set of states, which is the energy incoherent states. What does it mean to be energy incoherent states? It means that the initial system and the target system commutes with the Hamiltonian of the system. And if they commute with the Hamiltonian of the system, they are diagonal in this energy eigenbasis. So I can represent these states by probability vectors, such that they are the eigenvalues of rho and sigma respectively. And there exists a thermal operation mapping rho to sigma if and only if P thermal majorizes Q. I don't want to give you too much details about what does thermal majorizes means, but you can imagine that thermal majorization is a variant of the concept of majorization. So for example, in the limit in which the temperature tends to infinity, this concept here, in the limit in which the temperature tends to infinity, the thermal majorization reduces the case of majorization. Let's imagine the following scenario. Let's imagine that I have my system rho and some target state sigma, but I cannot achieve sigma via thermal operation. This operation is forbidden. I cannot achieve sigma. But let's imagine that there exists some sigma tilde in which I can achieve, and sigma tilde is very, very close to sigma in terms of infidelity distance. So in this case, we say that this is epsilon approximated interconversion problem, because you can go to some state which is epsilon away from the state that you want to achieve with this in terms of infidelity distance, okay? And we denote usually this transformation like this, P epsilon thermal majorizes Q, okay? Where this epsilon is the error of the transformation. In other words, we can say that we can go from sigma up to some error. We can always make this problem more interesting because so far I'm telling you about, let's say I have a single system and I'm going to another single system. But we can ask, how about we have a finite copies of a given system? So for example, any copies of rho. And then we ask whether we can achieve rho, whether we can achieve sigma, any copies of the state sigma via any copies of rho via thermal operation. So this problem was studied in 2008 by Camille and collaborators, and they gave second order rate for energy incoherent state. What does it mean? It means how many states you can achieve when you restricted this interconversion problem between energy eigenstates. They study also very rigorously the problem of irreversibility, which means let's imagine that we go from rho to sigma, whether is it possible to return to sigma again. And also they calculated the optimal values for the distillable work, the work that you can extract from a given system, and the work of formation, the work that is required to create some system. However, some questions remained. So for example, they study the interconversion problem between energy incoherent states. And how about for general states? So for example, how about for general pure states when your initial state is a general pure state? And is it possible to go beyond the second order asymptotic state interconversion? Why? Because the results holds when n tends to infinity and n has to be large. And what if I don't want to look for any large, for example? What is the optimal error of this transformation when I'm working, let's say, with 5 copies, when n is equal to 4 or n is equal to 7? And also, although I didn't show you, but I'm gonna show in the applications, there's a problem in quantum thermodynamics, which is very tricky, which is how to define work. But with the resource-theoretic framework, we can easily define work, I would say. But when you have finite copies of a given system, to define work, it's a little bit tricky, because work for us, as we will see, is usually defined in terms of a battery system. And when you have any copies of a given system, this means that according to this framework, you need any battery systems. But that it's a little bit difficult to interpret when you have any battery systems, because as I said, you have some error, you have some error, you have some fidelity of the battery, and it's difficult to try to understand what is this fidelity when you have any copies of a battery system. Okay, so that was that was one of the one of the questions that remained open. So, okay, I think now it's a good time to stop a little bit and see if you have any questions so far about the framework.
So, are there any questions to Alex?
Yes, I went a little bit fast in this first part about the resource theory framework, but if you have any question, please, you can ask.
It looks like it's not the case. So,
I have one.
Yes, so there are some. Yes, please.
Yes.
So who's speaking?
Ferishte.
Aha, Ferishte. Hello. Go ahead.
Okay, I want to know if satisfying the commutator between local Hamiltonian and the joint unitary operator is also necessary for the map E to have actually invariant state gamma.
Yes.
Necessary.
Yes, the condition that we know so far is that the initial system and the target, the initial state and the target state must commute with the Hamiltonian of the system. They are diagonal in the energy eigenbasis. And the unit, yes, and the unitary, the energy preserving unitary must commute with the total Hamiltonian as well.
Yeah, if the commutator satisfies, then we get a quantum channel with gamma as invariant state. But I want to know if inverse is true. For having a quantum channel with invariant state gamma, then we should have a joint unitary operator that that commutes with Hamiltonian.
Can I just jump in quickly?
Yes, please.
It's a more general family that you're asking for. Like just knowing that the Gibbs state is preserved does not mean that the unitary has to conserve energy. There are other maps that are Gibbs preserving, so that they have the Gibbs state as a fixed point, but they can't be realized as the thermal operations here.
Okay, so we add other restrictions to have those laws of thermodynamics, huh?
Yes, exactly. Yes. This time translation symmetry especially, yes.
Yeah, thank you very much.
Thanks for the question. And okay, so before I present you the two theorems, our two results, I would like to summarize what the questions that we want to answer and define some quantities which will play a role here. So first, let me start by defining what does it mean to do a thermodynamic distillation process. So a thermodynamic distillation process is an approximated thermodynamic distillation from a given state rho to some energy eigenstate rho tilde, such that this energy eigenstate, they are given here, where I'm pointing out, and and we will be it's approximated because we will be epsilon away from the target state. The final state is an epsilon away from the target state in terms of infidelity distance, this distance here. Okay, and another quantity.
Sorry, Alex.
Okay.
There are no misprint. So to have a really infidelity distance, As far as I
The
recall,
square root, right?
Square root.
Yes, exactly. Yes, sorry, it's missing a square root
Yes.
here.
Then it's a
Otherwise,
distance, because otherwise
yes,
it's like
it don't satisfy
semi-distance,
the
but does not
triangle
satisfy triangle
inequality.
inequality.
Yes,
Looks
that's
like,
true.
yes.
Thanks, Professor. I know this now when I was saying. And the other quantity that I want to define here is this dissipated free energy, rescaled by fluctuations of the free energy. So for example, this difference between free energies here are the work dissipated in this process, the work that you have to pay to go from a given state to another. Sorry. Oh, yes. Thank you very much. Thank you very much. And sigma here stands for the relative entropy between rho and gamma. And this quantity here are free energy fluctuations. Okay. So, oops, yeah. So basically, let's consider in the following scenario. Let's imagine that I have a composite system consisted by any different subsystems. Okay, so so I have a composed system composed by n subsystems, each one described by some state and some Hamiltonian, such that the total Hamiltonian is given by the sum of the individual states, and the states are product states, but they are different. Okay, so this will be my initial state. As a target state, I'm gonna have different energy eigenstates like this with different Hamiltonians. And let's imagine that we have m non-interacting subsystems. So my question now, not my question, but our theorem says that there exists a thermal operation mapping this initial state to the target state with an error given by this expression when n tends to infinity. So in other words, in the asymptotic limit at which n tends to infinity, the optimal error of this transformation is given by this expression here. Okay, so where phi is the cumulative normal distribution, which has this profile here. So basically here, I'm gonna mention this later, but basically here, we see that there is a trade-off between the work that is dissipated with the fluctuation. But how about, and let's imagine that I don't want to look for the asymptotic limit in which n tends to infinity, but I want to look for a finite n. So for example, n equal to 5. In this case, there is a thermal operation mapping this initial state to a target state with optimal error upper bounded by this quantity here. So again, this phi is the cumulative normal distribution. C is a constant called by Berry-Essen constant. And this W that appears here is the relative entropy skewness, which has that interpretation to be, thermodynamic interpretation to be the derivatives of the heat capacity with respect to the temperature when you are measuring between two thermal states with different temperatures. But what I want to emphasize with this theorem one is that we went beyond the i.i.d. cases, because here I have any different subsystems. I'm not working with copies anymore. Also, that this theorem guarantees a transformation error for a finite n. I don't need to take n to infinity anymore. And we see that there's some kind of trade-off between the work that you dissipated with the fluctuations, with the free energy fluctuations. In other words, let's imagine that for transformations with the same error, but with different fluctuations associated to the initial state, I have different amount of work being dissipated. If my initial state has more fluctuations, more work will be dissipated. Conversely, if the initial system has less fluctuations, less amount of work has to be dissipated to achieve the same transformation with this error. This will be more clear when I apply this theorem. Our second theorem, but let me make a comment here that the initial states, they are incoherent states, okay? And our second theorem is for general pure states. But now we have any copies of a general pure states. For example, this state here can be the state plus plus. And as a target state, I choose some m different subsystems, each one described by some energy eigenstate with its own Hamiltonian. And the theorem 2 states that there is a thermal operation mapping the initial state to the target state in the asymptotic limit, in which when n tends to infinity, with an error given by this expression here, as we saw in theorem 1. But now, let me point it out that we went beyond incoherent states, because here I'm dealing with general pure states. Again, we see this behavior between the work that is dissipated with the fluctuations that the initial state have. And also, let me mention that these fluctuations here, they are only energy fluctuations, because this state is pure, and you can show this. But the natural question is, okay, we see that there is a trade-off between the work that is dissipated with the fluctuations associated to the initial state, but why fluctuation-dissipation relation? What is a fluctuation-dissipation relation? And to answer this question, I would like to connect what I've been talking with a very nice idea in statistical mechanics. And let's imagine, let me show you this simple problem in which I have a thermal system, a thermal state, sorry. I have a system in the thermal state, and this system is, there's a bath at inverse temperature beta. They are in thermal equilibrium. And this system is described by some Hamiltonian H0. And what I'm gonna do is, I'm gonna perturb the system by changing its Hamiltonian. And then I'm gonna look to the response of this system after I perturb this system. But I'm gonna do this in a way that I'm gonna do a little perturbation in the Hamiltonian. So for example, I can write the Hamiltonian as a function of this lambda here in this way. And I'm gonna do a little perturbation because I want to use the framework of linear response, which is a well-known framework from statistical mechanics, to see the response of my system. Okay, if I do this, I will get that the dissipated work is proportional to the energy fluctuations that the system have when the system is in thermal equilibrium here. So basically, this can be very well captured by, if we remember about the Brownian motion. Let's imagine that we have a particle, and this particle is immersed in some liquid, and this particle is jingling because of the thermal fluctuations, and then I push this particle over across this fluid. When I push this particle will start to collide with the other particles. I'm gonna dissipate the kinetic energy, and this dissipation, it's connected with the fluctuations that the particle had when the particle was in equilibrium, okay? And what our theorem 1 and 2 says is basically a different way to state the theorems is, let's imagine that we fix some error of the transformation. So what our theorem says is that the amount of resource that has been distillated, the amount of work that has been dissipated, is directly connected with free energy fluctuations of the initial system. So we see a big similarity between these two different frameworks. And this is why we call these relations by fluctuation-dissipation relation, because the amount of work that I'm going to dissipate it is directly connected with the fluctuations that my system have when my system is, let's say, in the initial state row. Okay, so let me briefly apply the theorem 1 and 2 for two applications. And to do this, in order to do this, I would like to define, to show you how we define work in the resource-theoretic framework. So let's imagine that initially my system is composed by a given blue ball and a battery system, and this battery is empty. this battery is one charge. And then I ask whether there exists some thermal operation capable to thermalize the system while charging this battery. And the cost of this transformation, we define work, the amount of work that I can, let's imagine the amount of work that I can store in this battery system. And for example, I can imagine that this battery is a qubit in the grounded state, and after the thermal operation, I promote this qubit to I promote this qubit to the excited state, for example. And mathematically, I can represent it like this. So now we see that point that I mentioned about that framework that Camille introduced in 2018, which let's imagine that you have any copies of your system. You would have, according to that framework, any copies of a battery system again, because that framework was for copies of a given initial system. So now I'm gonna show you how we can correct this in a way that we have just a single system as a battery system, and how we can extract more information using our theorem about this setting. So let's imagine that I have any non-interacting subsystems, each one different from each other, but the last one I choose to be a battery system in the grounded state with this Hamiltonian here. As a target state, I throw away all of the systems. I kept this battery system, but now this battery system in the in the excited state. So now our theorem says that there is a thermal operation mapping the initial state to the target state with, there is a thermal operation mapping the initial state to the target state, and the work dissipated in this process is upper bounded by this quantity here. So in other words, to make this transition happen, we have to dissipate at least this amount of work. And the work that you dissipated is connected with the fluctuations that the system have in the initial, it's connected with the fluctuations that the system have. Also, our theorem says that the optimal error of this transformation for any n is upper bounded by this quantity here. And for example, to achieve the same transformation error from system with higher fluctuations, we need to dissipate more work for a fixed error. Conversely, to achieve the same transformation error from states with small fluctuations allow us to dissipate small amounts of work. And let me summarize. So basically, in this transformation, we have to dissipate some amount of work, and the dissipation is connected with the fluctuations that the initial system have. Again, the optimal error of the transformation holds for all n. N can be 3 or n can be 4. And here with this framework, this theorem allows us to have only a battery as a single system, like here. We don't need to have any copies of a battery system anymore. The second application that I wanted to show you is the optimal encoding of information, which can be recast in the following question. Let's imagine that it is given to us any copies of a given system row, and we are restricted to only perform thermal operations. So the question is how many epsilon orthogonal states we can encode into this given system. Epsilon orthogonal because they are orthogonal up to some error. Well, from this paper from 2018, sorry, the date is not appearing here, but it's from 2018. It's a paper by Millet Gu. We know that the optimal number of messages that can be encoded into a given system in a thermodynamically free way. Thermodynamically free way means using thermal operations is quantified by this quantity here. So in this paper, they gave an expression for the asymptotic limit. And with our theorem, we can give some second order asymptotic answer for these, such that the first term is the non-equilibrium free energy, and the second term is the relative entropy between rho with respect to the thermal state. Okay, so let me summarize about everything that I told you today, and we can discuss. So first, I show you that the theorem one allow us to work with different subsystems, although they are energy incoherent states, but they are different with different described by different states and different Hamiltonians. And this is very, very interesting for many reasons, because, for example, we can think in modeling a gas, for example, using this framework. Of course, that this is an optimistic thought, but we are evolving towards this direction. I also showed to you that we went beyond the incoherent states by considering general pure states, many copies of general pure states into energy eigenstates. And then I applied very briefly our results for the problem of work extraction and the thermal encoding of information. And I would like to finish my seminar by with a question, which is, and how about for general mixed states? Is it possible to do this? And this is one of the questions that we are working on. And yes, I hope we got it for next time I present to you again. So this, if you are interested in this work will appear on archive maybe next month, and it's that. So, oops, oh, I forgot it. Thank you very much. Yes, thank you very much.
Thank you, Alex. Thank you for a very nice talk and for finishing, yes, ahead of schedule. So it was not necessary to issue you any helpful warning. It's perfect, good time. Let us start now the discussion. Who would like to make a comment or ask a question? Please. Or you can also write by chat, but I